Hello everyone, thanks for coming. Today I will talk about improved bounds for the sunflower lemma. This is a joint work with Ryan Ewells from Princeton, Shahalawat from UCSD, and also Kevin Wu from Peking University. Kevin is also moving to Berkeley. Okay, let's start. In this talk, I'll go through these three parts. In the first part, I'm going to introduce the sunflower structure and also sunflower lemma and also sunflower conjecture. In the second part, I'm going to tell you our new improved sunflower lemma bounds. And in the third part, I'm going to briefly tell you our proof outline, which is based on a structure versus pseudo-randomness approach. Okay, let's start with some simple definitions. A set system is just a collection of sets. So we're just talking about sets. Okay, I hope this definition is clear. We call F a W set system if each set in F has a size at most W. Okay, I hope this definition is clear. Okay, so given a bunch of sets, S1, S2, up to SR, we call them an R sunflower if for any I and j, the intersection of Si and Sj is equal to the intersection of the whole sets. Okay, so this structure was introduced by Adelson and Radel in 1960, and in their original paper, they called it a delta system. Okay, so this is the original name, and the name sunflower was introduced by Deza and Franco in 1981. Okay, so okay, let me tell you an example. Let's say we have four sets: S1, S2, S3, and S4. Okay, and first, this is a three-set system because each set has size at most three. Okay, now if you're going to pick the first three sets, S1, S2, and S3, then this is a three sunflower because the common intersection of these three sets is X3. Notice that X3 belongs to every set. And how about and if you pick any two sets from this set system, say for example, you can pick S1 and S2, the intersection of S1 and S2 is exactly X3. Okay, so this is the same for S1 and S3 and S2 and S3. Okay. However, S1, S2, S4 is not a sunflower. Why? Because the common intersection, they have three sets, S1, S2, S3, and S4. The common intersection is empty set. However, if you're going to take any two, so for example, you can pick S1 and S2, then the common intersection of S1 and S2 is X3, which is not equal to empty set. Therefore, it is not a sunflower. Okay, so this is a simple example. Okay, then what is the sunflower lemma? In the same paper, Anderson and Radel, they proved the first sunflower lemma. Okay, so for any R, fixed R, any W set system of size at least W factorial times R minus 1 to the W contains an R sunflower. Okay. Notice in this lemma, we don't care about the domain, we don't care about anything. So we don't care about the ground set, or we can call it, we don't care about the universal set. So as long as there are enough sets, you can always find a sunflower. So this is the Adolf-Radel sunflower lemma. Okay, in think about for R is a constant, for example, R is 3, then this bound is roughly W to the W. This is the order of W factor. Okay, W factor is the main bottleneck here, if R for constant R. Okay, in this paper, they also believed this bound could be further improved. And Adelson and Radel made this conjecture is that for any R, there exists a constant C that depends only on R, such that any W set system of size C to the W contains an R3 sunflower. Okay, so again, think about R is a constant, then in the sunflower conjecture, this bound is constant to the W. However, in the sunflower lemma, this is W to the W for constant R. So this is the main gap. So in one hand, we can prove this is W to a W. On the other hand, there's a radical conjecture, the optimal bound should be constant to a W. Okay. So the sunflower structure is a pretty simple structure, and it's very nice. Okay, let me first quickly remark, for if you have a bunch of pairwise disjoint sets, then this set system is a sunflower. Why? Because if you pick any two of them, the intersection is empty set, and the common intersection is also empty set. Empty set is equal to empty set, so this is a spatial sunflower. Okay, pairwise disjoint sets are always nice and always easy to add. It have a nice structure. However, the sunflower lemma, sunflower structure is a kind of something like that. If you're going to fix the common pattern, I mean, we call it core, if we're going to fix this part, and the remaining part are pairwise disjoint. So therefore, it's also a nice structure. I personally, I feel this is the main reason that sunflower structure has many applications. So for example, it has a lot of applications in theoretical computer science. It has applications in monotone circular lower bounds, and has application in fixed parameter complexity, and also matrix multiplication lower bounds, and also data structure lower bounds. And also it has applications in graph cards, and of course, it has many applications in combinatorics because this is the original combinatorial structure and extra. So it's a very simple and very nice structure. Okay. So yeah, then what is our result in this paper? And our main result is an improved sunflower lemma bound. Okay. Let me first remind you the other shredded sunflower lemma is that for any R and of size of any W set of size W factor times R minus 1 to the W contains an R sunflower. Then before our results, this paper, then what was the best result? Is the result proved by Chaka in 2000. He proved any W set system of size W to W minus little OW contains a 3 sunflower. Okay, let's compare it to the original sunflower lemma. The original Edelstein-Rados sunflower lemma is on the bound was W factorial. Actually, it's roughly W to the W, and now it's W to the minus little OW. So basically the main improvement is the little OW term. So yeah. Okay. So then what is our bound? So in this work, we proved the following thing, for any fixed R, and for some constant C, there's a constant C. This okay, I want to mention, emphasize that this constant C does not depend on R and also does not depend on W. It's a universal constant. Maybe it could be 10,000 or something like that. You can figure out what is exactly from our proof. It's just a constant. Then any W set system of size at least C times R to the cube times log W to the log W to the W contains an R3 sunflower, contains R sunflower. Okay, this bound looks complicated. For a constant R, think about R as a constant, then we can just simplify this to roughly like a log W to the W. So actually it should be log W times log W to W. Okay. Anyway, by the way, some subsequent work of Frankel, Khan, Narayana, and Park. So there are two subsequent works. One is by the first one, FKMP. The second one is by Anup Rao. By combining their result, their idea, and now the best result, the best bound so far is they can improve this bound to C times R times log W to the W. So basically, they can improve the dependency on R from R to the cube to R. And also they can shave the log W term. So now this is the best result so far. Okay. And then as I mentioned, the sunflower structure is a very nice structure, and now we get an improved bound. And of course, there are some new applications. So the first application is a proof of the fractional expectation threshold conjecture. This is a conjecture from random graph theory and was asked by Talleyrand. Okay, so this result was proved by Frankston, Khan, Narayanan, and Park. And the second one is a new monotone circular lower bounds. And this is proved by Kavala, Kuman, Rossman. And the third one is an improved lifting theorem, and this is proved by Shahalovet, Ragumeka, and I. And this is from communication complexity, and also it gives a tight bound of DF compression. Okay, so this is not a very direct application, but this proof is based on the similar idea. Okay. This is by Shahalovet, Cohen, and I. This paper also published in Stock this year, and Cohen is giving the talk. Okay, and there could be more applications. Okay, now let me tell you the proof idea. This is based on structure versus pseudo-randomness approach. Okay, let me first introduce the structure part. So we're going to define by link. So given f, let's say the system f, and for any set t, t is not necessarily to be a set from f. Okay, so t just any set. Then the link is defined by defined in the following way. Is that the link of ft is defined that contains all. So we're going to first find all of the sets that contains t as a subset, and then we're going to remove the T, the set, the common pattern T. Okay. Now, a quick remark is that if F is a doublet set system, then Ft is a doublet minus T set system. Okay, the size of each set in Ft is reduced by, is decreased by T because we removed this part. We removed the set T. Okay, let me tell you an example, then maybe you can understand this definition more clear. Okay, let's say let's remind the previous example, we have four sets, S1, S2, S3, and S4. Okay, and we're going to choose T to be X1, for example, this particular set. Then what is the size of link Ft? What is the link Ft? Okay, Ft, okay, notice that T, remember that T is X1. Then there are two sets contains X1 as a subset, S1 and S4. Now we are going to pick these two sets. And we're going to remove T from these two sets. Now then we get S2, X3, because we pick S1, and then we're going to remove X1. Therefore, we get a set X2, X3. Again, similarly, so we have S4, which contains T, X1 as a subset. Now we're going to pick S4 and then remove X1, remove T, and we get X4. So we get the link Ft. The original set system was a 3-set system because each set has a size at the most 3. Now T, the size of T is 1. Now we get the link Ft is a 2-set system because we removed T. Okay. So this is structure part. And what is the pseudo-random part? We use the spread to capture the pseudo-randomness. We call a set system F is k-spread. If for every set T, the size of link T, Ft is at most k2 minus the size of T times the size of F. Okay, so basically we want to use the spread to capture the disjointedness. Think about disjoint sets. So if you have a bunch of set system which pairwise disjoint, then this is very spread. So this is the intuition. If you give a bunch of spread sets, so we use the spread to capture the disjointedness, and we can also prove this formally. Okay. what is the main lemma, and how could we formally state this intuition is the following lemma. So now I want to cite a Nuperal's result because the bound is more the bound is simpler. Okay, in Anoop's paper, he proved for any R, the fixed R, then any R times log W spread W set system contains R disjoint set. Okay, in our proof, in our paper, we get a similar bound. However, we get such like R to the cube times log R times log W. So that's the reason we get a slightly worse bound. But in Rao's result, he get a more clear bound, which is R times log W. Okay, so basically we use the spreads to capture the disjointness. Okay, in particular, it contains R sunflower because I mentioned if you get a bunch of disjoint pairwise disjoint sets, it's a kind of sunflower. Okay, again, on the other hand, in our paper, we also proved this is almost tight. Say we can prove the following thing: there exists a log W to 0.99 for the set system, which does not contain two disjoints, even for two disjoint sets, which means the log W is necessary. If we want to get our disjoint sets, log W spread is necessary. So basically, this is tight in this sense. Okay, so then, okay, from the previous lemma, the lemma from the previous slides, then we can prove the main lemma, I mean the improved sunflower lemma. So, okay, so this is the improved sunflower lemma is that for any R, in any W set system size at least C times R times log W, to the W contains an R3 sunflower, R sunflower. Okay, how could we prove this thing? The first is the pseudorandom case. If F is C times R times log W spread, then we have disjoint set, which means we're done in this set. In this case, okay, if not, then by definition, there exists F. There is a T such that the size of link Ft is very large. So by the calculation, we know the size of link Ft is at least C times R times log W to minus T times F. So by calculation, this is C times R times log W to the W minus T. Okay, notice the link Ft is a W minus T set system. Then we can apply induction on this link. Okay, so this is the whole proof. Okay, again, the main thing is the main lemma, and the main technical lemma is from the previous slides. Basically, is this lemma is that for any R times log W spread W set system contains an R disjoint set. Okay, so the proof of this lemma is based on an encoding argument, which was inspired by Rezbrov's proof of the switching lemma. So Hasta proved the switching lemma, and Rezbrov used the encoding argument to reprove this switching lemma, and now we get an inspiration from the Rezbrov's proof. Okay. Okay, so that's all. Thanks very much. So this is a short talk, and there are two long talks. One is given by Shahalovat at TCS Plus. You can check it here. The other one is given by me at IAS. Okay, thanks.